Hello, class. So we're continuing our session of videos titled Properties of Differential Equations. So in the previous video, we saw how to, given a differential equation, what's a general method for us to find a solution or various solutions. And we saw that the way to do that is by taking integrals, because the integrals cancel the derivatives out. Right? That's the general idea. Now, this session is called Properties of Differential Equations, so I want to start introducing some specific properties. Okay? So I'm going to give you two formal definitions here. Definition one, an ordinary. So basically, we're going to first divide differential equations into two types, ordinary and partial. So let's first see what an ordinary differential equation is. So an ordinary differential equation, which I'm going to just denote ODE, so DE for differential equation, O for ordinary, is an equation containing the derivatives of one or more unknown functions, dependent variables, with respect to a single independent variable. What this means is that if we have a differential equation, we could have more than one function that we're taking derivatives of. Right? We could have functions y, g, and actually let me call them these functions of x. We could have functions y of x, g of x, h of x, etc. We could be working with a lot of functions, but as long as we take derivatives only with respect to one variable, then it's an ordinary differential equation. Okay. Now, contrary to this, what's a partial differential equation? Well, it's basically the first part is the same. It's just an equation containing derivatives. Again, you could have more than one function you're taking derivatives of. That doesn't matter. What makes it a partial differential equation, which we're going to denote PDE, instead of an ordinary differential equation, is that you're allowed to take derivatives of two or more independent variables. What this means is that you could have functions of two variables, and I know you haven't seen this because this is something you would see in Calc 3, but you could have functions of more than one variable, which you would usually denote like this. You could say y is a function of x and t. So an example is something like x squared plus t squared. Y here depends on x and t. Now you could have various functions like this, etc. And what would be a PDE? Well, if you take derivatives of not only your variable x, let's say, but both variables. Let's say derivatives with respect to x and derivatives with respect to t. If those derivatives occur, right, so more than one variable, then that's a partial differential equation. Okay? Now, of course, like I mentioned, you haven't seen how to take derivatives of functions of more than one variable. So in this class, we're not really going to talk about PDEs. We're going to focus on ODEs because we do know how to take derivatives of functions of one variable. But it's important to note that PDEs are there because PDEs are a lot more useful for modeling than ordinary differential equations, ODEs. Basically, ODEs kind of limit you to one input, which could be position, could be time, could be income, anything that's changing. Well, with more than one variable, that's nice because now you can have more than one input. X can be position, t can be time, x can be the x-axis, t can be the y-axis. So it gives you more freedom. And in fact, when you're modeling things in space, right, so three-dimensional space, you at least need three variables. Right? One for the x-axis, one for the y-axis, and one for a third axis, which is usually goes, like vertical, like out of a paper. So like you have the x-y plane. So this is x, this is y. Then you have, I'm going to draw it like this, but then you have this other axis that's going perpendicular or going out of the paper, which you call the z-axis. So of course, if we're modeling things as accurate as possible in space, we want to account for all three spatial dimensions. Again, we won't be able to do that, but even with just one dimension available to us, just one variable, there's a lot of things that we'll be able to model. Okay. And the nice thing is that a lot of the things that we see in ordinary differential equations, just one variable, they actually translate very nicely into more than one independent variable. Of course, things get harder then, but the general ideas are the same. Now let's see an example here. we have a differential equation, g double prime of x plus h prime of x plus f of x equals 0. Notice that this is an ordinary differential equation because even though there's several dependent variables, several different functions, in this case g, h, and f, we're taking derivatives with respect to one single variable, which in this case is x. So taking derivatives with only one single variable, that tells you, okay, that's an ordinary differential equation. Contrary to this, if you see a differential equation like this, now here, let me just very quickly introduce this notation. So this is called partial derivative. So partial derivative of u with respect to t is basically the notation if you want to take the derivative with respect to a variable of a function of more than one variable. Right? So here u is a function of two variables, x and t. So if we want to write the derivative of u with respect to x, since there's two variables involved, you can't really write du dt. That's not correct. So instead, you introduce this new notation that's called the partial derivative, which uses this symbol here. Again, that's just notation-wise, don't worry too much about that. The point is, here you see that even though there's only one function, right? Remember, the number of functions doesn't matter. You can see that there's derivatives with respect to more than one variable. In this case, there's derivative with respect to t and derivatives with respect to x. So you're taking derivatives with respect to more than one independent variable. This is a partial differential equation, right? And that's the difference. Now, this is a very important partial differential equation. So let me erase this here. This PDE is used to model diffusion of heat and along a one-dimensional solid, right, as time passes. So basically think of having some sort of one-dimensional solid, maybe something that resembles kind of like a pipe, like a straight pipe. And then you have a heat source, maybe on somewhere on the pipe, and then you want to track how is this heat moving around the pipe. Well, then use this sort of differential equation here. So you can actually model that diffusion of heat using something that looks like this. So again, we won't be able to do partial differential equations because we don't know the theory yet, but we will be fine with working with ordinary differential equations. Again, that's the first thing or way we're going to be differentiating, or let me say it another word, or identifying differences between differential equations. Well, we have type here, which I introduced as either ordinary differential equations or partial. Again, ordinary means derivatives with respect to one independent variable. Partial means derivatives with respect to more than one independent variable. And again, our focus is going to be ordinary differential equations.